All right, this is a video with some requested questions for the review for tomorrow's exam. So we're looking at number 21, part B. We're supposed to be solving the following equation. It has a natural logarithm in it. So we're going to be isolating this because that has our x in it. So the first step here would be to divide both sides by that 4 to get rid of the part in front of the natural log. So if we divide that over, that'll be 3 on the other side. Then we have to remember that this is a hidden base e here. Remember, this is log base e. So when you're converting a natural logarithm that is equal to a number to exponential form, we know that e, the base, to the answer of the log, which is your exponent, equals the argument. So it's e to the third equals x minus 1. The final step to solve for x, now that it's no longer in the natural log, is to add the 1 to the other side. So e to the third plus 1 equals x. There is our solution in an exact form. Now, if it did say on the directions, which it doesn't, if it said, round, you could use your calculator for that part. But it says just solve, so that means usually exact form. Okay, so let's move down to another question. We also want to look at number 23. There were 2 requests for this one, E and H. We're finding the indefinite integral. Okay, so to find the indefinite integral, the first thing you want to look at is it a basic just polynomial terms or terms with powers? If that's the case, then we can just do our individual power rule for each of those adding or subtracted terms. If you see something a little more complicated, which we'll see further down, you might think about, is it a U substitution problem? So let's look at these first. I would first rewrite this as a rational exponent. So this would be the integral of t to the 2/3 plus t dt. So these are individual separated by a plus, so we can do each one individually when we do the integration. So remember, to do the integration, you add 1 to the power. So that would be t to the 2/3 plus another 3/3 would be 5/3. Normally, we then divide by the power, but because it's a fraction, we're going to multiply by the reciprocal. So we just write it like this. Plus t to the first becomes t squared. You divide by the new power, so that's by 2. And then remember, we don't know if there was this is going backwards. You're taking something and going to what was it before we took the derivative. So anytime you go backwards, you don't know if there was a constant that had been fallen off after taking a derivative. So that's why we put the constant of integration plus c. And that is required. You will lose points when doing an indefinite integral if you don't put the plus c at the end. Okay, let's look at h. This one is also separated by a plus, and these are 2 of our special integrals. Sorry, excuse me. So we have 1/x plus e to the x dx. You don't need the parentheses around it. They just did that to emphasize these. But the integral of 1/x is natural log of x in an absolute value. That is a special one you have to have memorized. And e to the x, its antiderivative or integration is just itself. So as long, and then we need our plus c. But as long as you don't have anything weird in the exponents or anything weird down here, these are the basic general rule. Now, if this had been e to the 2x, that's a little different. That's not basic e to the x. We would need to do a u substitution. So you'll see that kind of in another group of problems a little further down. All of these were basic power rules or the special cases. Actually, that's not true. I see that G had a 7x in that one. So I might do that one just for reference. So that one's going to need a U substitution. So let's look at G. So this one would be, I'm going to bring it up a little bit. We have 3x to the 4th dx. I actually separate them when I see one part that has a U substitution and the other part didn't have a U substitution. This is a basic power. This has a weird 7x in it. So I like to separate, and you're allowed to separate your integration as long as you keep the sign in between them so that we can focus on them separately. All right, and then this also has a dx on it. Remember, and this is something I want to mention. If you leave off symbols, the integration symbol and the dx symbol before you actually take the antiderivative, you don't technically have the correct notation. You only drop this and the dx once you've taken the antiderivative. So for this first one, it is pretty straightforward. It's just, and so I'm going to do this one probably last, but it's just going to be a power rule. On this one, we're going to need a u substitution because this 7 doesn't really make this just a basic x. So when you're doing a u substitution with an e, you let u equal the exponent, then du has to be the derivative of this dx. So that's going to be 7 dx. Now notice I have a 2 here and I need a 7 dx. So one thing you can do is pull the 2 out to the front just to get that out of the way. I'm going to bring my other stuff over as well, because that's not what we needed. And then we know that if we put a 7 here to make that 7 dx, you have to counter it by dividing by 7 on the outside. So now we're going to be able to do our substitution. So this part right here is just going to be 3x to the 5th over 5. I already know that part. And there'll be a plus c, but I'm going to add it on at the end. This one I'm going to change to u substitution. So notice I'm not getting rid of the integral yet. This is e to the u du. Now I can do the integration for that. Just going to keep bringing this down. So that's 3/5 x to the 5th, or you can write 3x to the 5th over 5. Either way is fine. Minus 2/7 e to the u's antiderivative is e to the u plus c. The only thing wrong with my final answer is this doesn't need to be u. It needs to go back to being 7x. When you're doing an indefinite integral, it is required that you back substitute because your answer needs to be in terms of the original variable. So there is my answer for that one. So I added that one in. Nobody asked for that one, but that is slightly different than h because of the 7x. So it makes it a little more complex. All right, I had a question about number 24. So let's look at this one. This says find the particular solution that satisfies the differential equation in an initial condition. So anytime it says particular solution, that, remember we talked about that in class, that means you're going to be doing the integration or the antiderivative, and then you're going to be solving for the plus c part using the ordered pair. And that will give you then an exact equation that we know has the derivative 8x to the 4th and goes through the specific point. So you only use the point on the second part of this problem. So we call, remember, the family of functions that all have f prime of x as their derivative, big F of x. That's the antiderivative notation. So this is going to be what we do. We take the antiderivative of 8x to the 4th dx, so integrating it over dx. Then we remember to write our plus c once we do that. So that's going to be 8 raised the power by 1, so x to the 5th divided by the power plus c. They told me that when I plug in a 1 for my x, my y, which is our big F of x in the function, is 2. So I'm going to come over here and write 2 equals 8 times 1 to the 5th over 5 plus c. That's just going to be 8/5 plus c. We'll subtract that over, so we want to get a common denominator. So that'll be 10/5 for 2 minus the 8/5 equals c. So it looks like c is 2/5. Now my final answer is to plug c back into the big F of x. Now, if you want to, you can change it to little f of x now, because that is technically the notation here is little f prime and little f of 1. But remember, the big F of x means the family. That was that when we talked about antiderivatives, we said there's a whole vertical shift family of functions, essentially, that all have the same derivative, but just a different constant. So this would be 8x to the 5th over 5 plus 2/5. So there's my specific or particular solution to this situation. All right, let's look at 26. I was asked to do part A. This one is the classic, these all here are also going to be classic U substitutions. because there is a complexity here. It looks like there's a chain rule involved or some kind, it almost looks like product or quotient rule. A lot of times those are places where you want to look and see, can you do U substitution? So we're going to let the most complex portion, which is the part under the radical, be our U. So we say, okay, if U is 1 minus 3x squared, then du would have to be the derivative of this. Derivative of 1 is 0. This would be negative 6x dx. Now I have a 2x dx, so I'm close, but I need a negative 6. So I'm going to be multiplying the inside of this by negative 3, which means I have to divide to counter it on the outside, so a negative 1/3. So I'm going to rewrite that as negative 1/3, the integral of, and I like to write my stuff in a different order sometimes since it's all multiplication here, just so I can see now that I have my pieces that I need. So this is the 2x times the negative 3 that was inside. Okay, so now I have my place to do my U substitution. So this is the square root of U du. We can think about that being U to the 1/2, just so we can see the power better. And then for this, we're doing our power rule. So this would be negative 1/3 times, and then we raise this one power. So that's going to be 3/2 when we add another 2/2 to it. And then remember, we multiply by the reciprocal when it's a fraction, plus C. Now, when we do this, and this should all go to this, but when you distribute a negative 1/3 to C, we just still call it C because C represents any constant out there. So it's an infinite number of possibilities. So this is just negative 2 U to the 3/2 over 9 plus C. And then our final step is to replace that back as the part with the X. So negative 2, 1 minus 3x squared to the 3/2 all over 9 plus C. So there's that one. Okay, so then I think that was it for the questions that were asked so far. So as you're working through this, if you get me your request pretty early today, I should still be able to make another video possibly. It just depends. If it comes to me super late tonight, I probably won't. But remember, I have office hours tomorrow before class. So from 9:30 to 10:30 in my office, which is right near our room. That's 213. You can come see me and ask me extra questions. But also we'll have a little bit of review time before we take the test as well. So just make sure you reach out if you have other questions. I'm going to go ahead and post this video. And I did, hang on one second, let me pause this. Yeah, I wanted to check something real quick. I did have a question about how many questions are actually on the part 1 that we're taking tomorrow, and that is 12 questions. Now that doesn't seem like a lot, but some of them have parts. So like obviously we're probably going to ask you to do more than one derivative or maybe more than one integral, give you an opportunity to show some of your skills. We'll probably ask you to do more than one definite integral where you evaluate them. So there'll be some of these where there are multiple parts, especially the big graphing problem. That is absolutely going to be on there. On the test, we're a little nicer than this. We actually kind of lead you through the parts like we did in class. So if you want to look back at the notes and the worksheet that we did in class on this, where I kind of had what is the relative extrema, what's the increasing, decreasing, where we kind of led you through the process. That'll be a good way to look at this one and kind of say, okay, do I know how to do all the pieces? So yeah, just make sure that you prep really well for this specific part of the review. This is numbers 20 through 32. So we're going to pick 12 questions, which means it looks like there's one of every type here because that's 12 questions total right there. So make sure you are good on those. And that's it for this video.